Electrochemistry is what this chapter is about. It is the study of these redox reactions, right? Our reduction oxidation reactions that are going to produce or require an electric current. So there is the flow of electrons, right? We are going to get some current. This is what batteries are. They are a flow of electrons that cause the current to happen. That is electrochemistry. So we call an electrochemical cell that converts chemical energy into electrical energy. That is our electrochemical cell. That is a battery. We are literally taking some chemical, right? It is using energy, it is giving off energy, and it's converting it into electricity, electrical energy. It is happening in an electrochemical cell. If this is spontaneous, so if this reaction is going to happen no matter what, this we call a voltaic cell. We can also call it a galvanic cell, but this is if it's spontaneous. You'll hear me say voltaic cell. If it's not spontaneous, so that means we need to add some electrical energy to make it spontaneous, that is an electrolytic cell. So if it's spontaneous, it's voltaic. If it's non-spontaneous, it's electrolytic. Here's a spontaneous reaction. So if we took zinc solid, and we put it in a solution of copper 2 sulfate. So as you can see, copper 2 sulfate is blue in color. That's what copper ions look like. They're blue in color. What is happening? Well, over time, it looks like this. So what happened? Well, let's look at the reaction. So here's zinc solid plus zinc 2 plus copper 2 plus. What's happening is here are solid atoms of zinc. 2 electrons are coming off, and they are adding to the 2 plus of the copper. So now our copper 2 plus 2 electrons would be copper solid. So now our copper ions in solution are becoming copper solid. So this solid is now coming on to this zinc rod, the zinc strip, now has all of the solid copper that came out of solution. But when those 2 electrons came off of that zinc, now what happened? That zinc now is zinc 2 plus. So now we have zinc 2 plus ions in solution. So what ends up happening is we start with this, right, zinc strip in this copper sulfate solution. The zinc strip, zinc starts coming off, right? Zinc now goes into solution. So we started with zinc solid, zinc now goes into solution. So now our zinc, we have less solid form. And what happens is the copper 2 plus in solution now goes on to the zinc rod. It solidifies. We get solid. So it doesn't necessarily need to go onto it. Yes, you can see there's some on the bottom. It's just going to become solid. And it's easy for it to happen here because this is where those 2 electrons came off to make it into a solid. But it could be anywhere. The solid could be down here. So at the end, we now have a lot of copper solid, right, and zinc 2 plus in solution. As you can see, it was very blue in color to begin with. The blue decreased, right, because that was the copper. So when the copper became a solid copper form, right, it's no longer this blue color. It's more of a black color. So when we talk about our voltaic cells or our galvanic cells, those are our spontaneous redox reaction. So that was a spontaneous reaction. If we literally set that in there, we would see this happen, okay? We don't need to add any energy to it. It will happen no matter what. This is spontaneous. So that's what we're talking about with our voltaic cells. Let's talk about the electrical current. So electrical current is the amount of electric charge that passes through a point in a given period of time. So electrons, normally what we're talking about is our electrons. We can be talking about electrons flowing through some wire, or we can talk about ions flowing through some solution. The electrical current will be how much of that charge, whether they're electrons or ions, passes through some point in a given period of time. That is how we would get our electrical current. Our redox reactions, we know, involve the movement of electrons from one substance to another, right? Our electrons are going to they're going to be lost from whatever is being oxidized, right? And they're going to be gained by whatever is reduced. So they are exchanging electrons. Those redox reactions generate an electric current because there is a flow of electrons, right? These electrons flowing through a wire, we can look and figure out the electrical current. A spontaneous redox reaction that does not require external energy would have a delta G that is negative. So a Gibbs free energy that's negative, right? We already talked about before, is spontaneous. Voltaic or galvanic cells produce electrical current. So we will get some electrical current from a spontaneous redox reaction. In order to use that current, though, we would need to place the oxidation separate from wherever our reduction is happening. We would need to have two separate cells in order for us to actually get that current. So what we would do is we would have half cells. We would have our half reactions separate from each other in half cells. So our oxidation would be one half cell, our reduction would be another half cell. We would then need some electrical circuit. So a circuit has to be closed, right? So what we would have is we would have electrons that are flowing through a wire. We would also have ions flowing through a salt bridge. We would connect the flow with an electrode that is able to transfer electrons. So this electrode can either be an external circuit or it could be a metal or graphite electrode. So what's going to happen is there's going to be the exchange of ions between the two half cells via a salt bridge. I want to show you the picture. This is what it looks like real quick. Here are the two half cells. This is the oxidation reaction happening over here. This is the reduction reaction. On the left, oxidation. Oxidation has the anode, okay? These are vowels, oxidation, anode. So oxidation always occurs at the anode. We always draw the anode on the left for a voltaic cell. Oxidation, anode on the left. So at the anode is where the electrode occurs with oxidation. So oxidation occurs at the anode. The anode is the electrode. Anions are attracted to this anode. When we were to connect our battery, we would connect the positive end. And it is also going to lose weight because we said before, right, that zinc was losing itself, becoming into solution. So that's what's happening here. This is going to lose weight and it will go into solution. At the cathode, that's where we get reduction. Cations are attracted to it. So cations at the cathode. And we would connect the negative end of the battery and it would gain weight. We could also do electroplating. So here we go. Here is our cell. Let's look. Oxidation occurs at the anode, right? Anions are attracted to it, so negative end. So what's going to happen is our anode, we have this solid zinc in solution. This is our anode. In the solution is zinc 2 plus, right? That's zinc 2 plus. So this is oxidation. This zinc is going to lose electrons and become zinc 2 plus. So these electrons are going to come off the zinc. This zinc solid is going to reduce in size to come into solution. What's going to happen is those two electrons, how do these two electrons get over to this copper? Well, the two electrons that are lost from the solid are going to flow through this wire. So it flows through this wire and goes onto the copper. So now we have copper that has extra electrons in it. So now if it's got these two electrons that came through this wire, that means now some of these copper solution can end up going onto the copper and become a solid. So now this is going to gain in weight, right? Our copper solid is going to get bigger. Our zinc solid is going to get smaller. What needs to happen though is we have our electrons flowing through our wire. We need to have a closed circuit, right? We need to be able to generate electricity. We know that, if you were to install a light bulb, you have to have a closed circuit. In order to get this light bulb to light up, we do need a salt bridge. So a salt bridge, our anode, right, is where we have our positive end of our battery. So we need to have negative ions coming to it, okay? Because we have positive ions in solution, so we need to have negative salt bridges, negative ions. Our cations will end up going to our cathode, right? This is the positive end. Our cations are going to our cathode. So that overall we have a closed circuit. This salt bridge is very important. If we got rid of the salt bridge, it wouldn't be a closed circuit, right? It would not be a continuous flow. So what happens is this reaction is spontaneous. It will light up the light bulb. So overall, anode, oxidation, the anions are attracted to it. Cathode is reduction, where our cations are attracted to it. Our flow of electrons, oxidation loses the electrons and it goes towards the cathode, where we have reduction happening. So at the anode, it's losing those electrons. So our zinc solid, right, is losing 2 electrons, so it comes off into zinc solution. At the cathode, we have electrons coming in, and so it's pulling stuff out of solution.